Hello, this is the section 1.3 lesson. In section 1.2, when we looked at the theoretical approach, we saw that to calculate a theoretical probability, we didn't actually have to list all of the outcomes in the sample space or in the event. All we needed to do was count the number of outcomes in each. And so in this section, we're going to look at some simple techniques for counting the number of ways that we can do this. Okay. And so this is all based on what we call the fundamental counting principle. And that says, suppose we have a choice to be made which consists of a sequence of two sub-choices. So we have to do one choice and then a second choice. If the first choice has n1 options and the second choice is n2 options, then the total number of options for the overall choice is n1 times n2. So all you have to do is multiply the numbers of sub-choices, and that gives you the total number of ways you to make the overall choice. And of course, this could be extended to more than two sub-choices. It's just stated here, two sub-choices for convenience. Now, when using this fundamental counting principle, we're going to use factorials a lot. And we've all seen factorials a lot, but just to refresh our memory, here's the definition. Let n greater than 0 be an integer. The symbol n factorial is, by definition, n times n minus 1 times n minus 2, all the way down to 2 times 1. And then for convenience, we define 0 factorial to be equal to 1. Okay. And so let's do a simple example of this. Suppose an outfit consists of a shirt and a pair of pants. How many outfits can we choose? Well, for argument, let's suppose that we have 6 shirts and 4 pairs of pants. So when choosing an outfit, I first have to choose a shirt and then a pair of pants, or the other way around, it doesn't really matter. So those are our two sub-choices. And so by the fundamental counting principle, we have 6 times 4, which is 24 different outfits that we can choose. So that's all there is to using the fundamental counting principle. Okay. Now, there's really 3 types of counting problems that we're going to look at in this section. The first is what we call a permutation. So to define that, suppose we are choosing R objects from a set of N objects, and these requirements are met. So we've got a large set of R objects, and we're going to choose a smaller number of those, and these requirements are met. So number 1, the N objects are all different. Number 2, we are choosing the R objects without replacement. Now, without replacement means that we're not going to be able to choose the same object more than once. And then third, this is an important one, the order in which we make the choices is important. So if those 3 conditions are met, then the number of ways the overall choice can be made is called the number of permutations of N objects chosen R at a time. And it's denoted NPR, and we can calculate it using this formula, n factorial divided by n minus r factorial. Okay. So as an example, suppose there are 15 members of a town council, and they have to choose a committee consisting of a chair, a co-chair, and a secretary. How many different committees are possible? Okay. Well, notice that we have a large object of 15 people to choose from. They're all different, and we're choosing them without replacement, meaning we're not going to choose the same person twice. And we're going to choose 3 of those people. And we can interpret this as though the order is important. We can think of it as like the first person we choose is the chair, the second person is the co-chair, and the third is the secretary. Now the problem doesn't explicitly state that, but we can interpret it in that way. And so this is a permutation problem. So the number of ways is 15p3. If we plug things into our formula, there's what we get. We do those calculations, we get 2,730 different committees. Okay. Now the second type of counting problem we're going to look at is called a combination. And this is very similar to permutation, but there's just one very slight difference. So suppose we are choosing R objects from a set of N objects, and these requirements are met. Okay, so same basic scenario. Number 1, the N objects are all different. Number 2, we're choosing without replacement. And then number 3, the order in which the choices are made is not important. So that's the only difference between a permutation and a combination. In a permutation, the order is important. In a combination, the order is not important. Okay? So then the number of ways the overall choice can be made is called the number of combinations of n objects chosen r at a time, and it's denoted NCR, or it's also denoted like this, n over r. It looks like a fraction, but there's no horizontal line, and it's in parentheses. And we can calculate it as n factorial divided by r factorial times n minus r factorial. Now, the book discusses the theory behind this, but we're not going to go into it here in this lesson. So as a simple example of this, suppose good old Martin is going to choose 3 friends from a group of 9 friends to be his roommate for next year. In how many ways can he make the selection? Okay. So notice that we have 9 people to choose from. They're all different. We're going to choose 3 of those people. We're going to do it without replacement, because he's not going to choose the same person twice. And the order is not important. There's no distinction between the different choices. It's not like one person is the chair and the second person is the co-chair or anything like this. All of these people are equivalent. So this is a combination problem. And so the solution is 9C3, which we plug things into the formula and we get 84. So 84 different ways he can choose his friends. Now, in this next example, we're going to put together combinations, permutations, and the fundamental counting principle. So, local college is investigating ways to improve the scheduling of student activities. A 15-person committee consisting of 5 administrators, 5 faculty members, and 5 students is being formed. A 5-person subcommittee is to be formed from this larger committee. The chair and co-chair of this committee must be administrators, and the remainder will consist of faculty and students. How many different subcommittees could be formed? Okay. So this problem looks pretty complicated, so the first thing we got to do is weed through things to understand what's going on. And the important things to note here is that when choosing this subcommittee, there's really 2 sub-choices we have to make. Number 1, we choose 2 administrators from a group of 5, and one of those administrators is going to be the chair and the other is going to be the co-chair. So in that case, order is important. And then number 2, we're going to choose 3 faculty and students from a group of 10. Now there's no differentiation between those positions there, so order there is not important. Okay? And so the number of ways to make that first sub-choice is 5p3. It's a permutation problem. The number of ways to make that second sub-choice is 10, choose 3. It's a combination problem. And so using the fundamental counting principle, we multiply those 2 numbers to get our final answer of 2400. Now, our last type of counting problem isn't one where we're necessarily choosing objects from a larger group. All we're doing is rearranging different objects. So suppose we are arranging n objects, where n1 of them are identical, n2 of them are identical, so on and so forth. Then the number of unique arrangements of the n objects is given by this number, or this formula. N factorial divided by n1 factorial times n2 factorial up to nr factorial. And so to illustrate this type of problem, let's look at this example. How many words, quote unquote, can be formed with the letters in the word Mississippi? And so by word here we mean simply an arrangement of those letters, not necessarily a word that can be found in the dictionary. So we're going to take these 11 letters in the word Mississippi and rearrange them to find a different word. Okay? Now notice that not all of those letters are different. And in fact, we've got a lot of them that are the same. So note that we have 4 S's, 4 I's, 2 P's, and 1 M. And so the number of ways that we could arrange these is 11 factorial divided by 4 factorial times 4 factorial times 2 factorial times 1 factorial. And we do that arithmetic, we get 34,560. So that's the number of words that we could form. Lastly, let's talk about how to do these calculations on the calculator. Formulas for permutations and combinations are built into the calculator. So for example, let's calculate 15p3. So the first thing to do is to enter the number 15 at your blank home screen. And then go to the Math menu, the PRB submenu, which stands for probability, And then we see there option 2 is NPR, option 3 is NCR, and option 4 is the factorial symbol. So if I wanted to enter this formula manually, I could use the factorial symbol there. But we want to do NPR, so we're going to choose option 2. And when you do that, it will paste this NPR back at the home screen. And then you simply enter the number 3 and press enter, and it gives you the result. Now we can do combinations in the same way. For instance, to do 9C3, we'd enter a 9, and then at the probability menu, we'd choose option 3, enter a 3, press enter, and you get your answer. So that's all there is to calculating permutations and combinations on the calculator.